Welcome to Summarize Science. Today, we're looking at a fascinating paper that dissects a hypothetical, but terrifyingly plausible, full blackout of the Iberian Peninsula. On April 28, 2025, the power grid for Spain and Portugal experienced a complete collapse in just 30 seconds. This event was unique because it wasn't caused by a storm or a typical overload, but by something much stealthier, a sustained high voltage or overvoltage. The morning started with the grid running on 82% renewable energy, which is great, but also presented unique challenges. Minor oscillations, like wobbles in the system's stability, prompted operators to take action. They followed standard procedure, making adjustments to stabilize the grid, and for a while, everything seemed fine. But these fixes had an unintended and invisible side effect. The main problem, as the researchers identified, was a critical observability gap. Think of it like this: the grid operators were monitoring the main highways of the power system, where everything looked normal. But the problem was brewing on the local side roads, at the collector stations where renewable generation connects to the grid. This diagram shows the critical mismatch. The transmission voltage that operators could see, in blue, was safely below the limit. But the hidden collector voltage, shown in red, was creeping into the danger zone. At 12:32 p.m., a single transformer tripped because of this hidden high voltage, and that was the trigger for the cascade. The loss of that one piece of equipment removed its ability to absorb reactive power, a bit like removing a shock absorber from the system. This caused voltage to rise elsewhere, tripping more equipment in a disastrous positive feedback loop. Now, many people might immediately blame the high level of renewables, but the paper argues that's a misdiagnosis. These charts show that with proper, continuous voltage controls, the system could have remained stable even with 100% renewables. The real failure was that the existing generators weren't providing that continuous control as required. Even more paradoxical was what happened next. As the system spiraled, an automated safety measure called under-frequency load shedding kicked in to prevent a frequency collapse. This system is designed to save the grid by cutting power to certain areas. But in this specific case, shedding that load also removed its ability to consume reactive power, which poured fuel on the overvoltage fire and accelerated the final collapse. The very system meant to save the grid helped destroy it. The researchers successfully replicated this entire chain of events on a test system, showing how the operator actions slowly raised the system's voltage before the first trip sent it all tumbling down. So, was this a black swan, a totally unpredictable event? Or a gray rhino, a highly probable threat that was visible but ignored? The paper concludes it was mostly a gray rhino. The vulnerabilities, like poor voltage control and gaps in monitoring, were known and had been documented years earlier. So to recap, the blackout was caused by a convergence of factors: operators taking actions that inadvertently weakened the grid, a hidden voltage problem they couldn't see, and a safety system that backfired spectacularly. The key lesson is that as our grids evolve with more renewables, we need smarter tools and better visibility to manage these new, complex dynamics. We can't rely on old playbooks to manage the grid of the future. Thanks for watching Summarize Science.